Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem, minimum height trees. We're given a graph that is going to be connected, but it's not going to have any cycles within it. So by definition, it is going to be a tree. And this graph is going to consist of n nodes labeled from 0 to n minus 1, and we're going to have exactly n minus 1 edges. And that's a very special number if you are familiar with graphs, because for us to have n nodes and have them all be connected and not have any cycles, we are pretty much required to have exactly n minus 1 unique edges. Because if you look at this graph over here, if I were to add a fourth edge, then I would be introducing a cycle no matter what. And also, if I were to remove any of the edges, I would be disconnecting the graph regardless of which edge I remove. So that's a special number. But continuing, if we were to pick any of these nodes as the roots, which you can see that they've pretty much done here. So this is the graph that we were given, 4 nodes, and these are the edges. Consider if 0 was the root of the tree. Well, the height of the tree would then be 2. If 1 was the root of the tree, the height would be 1. If 2 was the root of the tree, the height would again be 2. Same thing over here, the height would be 2. So among all of those, we want to return the root such that the height is minimized. This was 2, this was 1, this was 2, and this was 2. So this one is the only one that minimized the height. Therefore, we return a list with 1 inside of it. Just based on that alone, it's not too difficult to at least conceptually arrive at the brute force solution. And that would be doing a graph traversal, whether it is DFS or BFS. And basically, like they did with this picture, consider every single node as the root, figure out what the height of the tree would be then. With BFS, we'd kind of do it layer by layer. So here the height is 1 and here the height is 2. So that's how we would do it. We could also do DFS and then figure out, okay, the path here was 2. The path here was also 2. So we would take the maximum of whatever the paths are, and we'd get 2. We would do that for every single starting point, and then among all of those, we'd figure out which was the minimum. The minimum was 1, and only a single root gave us that height, so then we'd return that. Now, the problem with this brute force approach is it's not very efficient. What do you think the time complexity is? Well, if we have n nodes, that means we have n starting points. We're going to run this graph traversal, regardless of which one we choose. We're going to run it n times on this graph. Doing this graph traversal is going to require us to visit pretty much the entire graph. So therefore, the time complexity here is going to be big O of n squared, where n is the number of nodes. Now, typically in a graph, the traversal is going to be the number of edges plus the number of vertices. But remember, the number of edges here is pretty much proportionate or equal to the number of nodes. So we don't really have to consider that in terms of the time complexity. So we just can say n squared. Okay, that's for the brute force, but how can we make this more efficient? I will admit this is a pretty hard problem for a medium graph problem, so don't feel too bad if you weren't able to figure it out by yourself. So there's actually 2 solutions for this problem. I'm going to end up coding the one that I think is easier to code up, but that's kind of subjective, so I'll at least conceptually explain both of the solutions. Before we even do that, let's just consider how would the height be minimized. Suppose we just have a single node. Okay, that's simple enough. This is going to be the root. Now, if we introduce 2 nodes, I guess both of them are the root, right? That minimizes the height. So if this is the root, then the height is going to be 1. If this is the root, the height is also going to be 1. Kind of looks like a face, but okay, let's ignore that. Let's make it more interesting. Let's add a 3rd node, and let's do it like in a straight line, because regardless of where we add it, it's going to be a straight line anyway. But now we see the length of this entire thing is 2. So if this were to be the root, the height would be 2. If this is the root, the height is also 2. But here, it's special. The height is going to be 1. So this would be the root of the tree. Now we can get more interesting. Now we can start adding nodes either here or here or here. We have 3 choices of where we add nodes, and that's because we have 3 nodes. Any node can be used to add a neighbor to that node. So even though we're thinking about this in terms of trees, ultimately this is still a graph. So I think it's useful to think about it in terms of neighbors rather than children. So what happens now? If we add a node here, what exactly did we do? Let's just look at it for a second. Remember, the height of this guy over here is 2. If we add a node here, we're kind of increasing the height to 3. Over here, the height was 1 because we go that way or we go this way. But by adding a node here, we're increasing the height to be 2. Also, from the perspective of this node, the height actually doesn't change because the height here was 2. And if we add a node here, the height in that direction is 1. So we would take the maximum, and 2 is going to end up being the height from here. Okay, so in that case, a node here, that would mean that these two are the roots of the minimum height trees because both of them had a height of 2. So we're just playing around with this so far, just trying to build a little bit of intuition. Now let's try to consider this case. We could add a node here, but that'd be pretty much the exact same as I just showed you, except on the other side. But let's try it here in the middle. This is special because the height of the tree does not change. And that's going to be true if I add another one here and another one here and another one here. And now it starts to get a little bit intuitive what we're doing. This is not changing the height. I could add a million nodes and I'm not changing the height. But if I now add a node here, just like we did before, just like we did with that thing, it's going to increase the height. Before I do that, we still have a single root node, and the height, of course, is going to be 1. If we consider any of these as the roots, the height is going to be 2, this way or the other way, right? But now when I add a node here, this is still the root because the height is now 2. It's been minimized. This is not going to be the root. Its height is going to be 1, 2, 3, but this one is also the root now because look, distance here is 1, okay, but distance here is 2. Minimum is 2. Okay, so now we have 2 roots just like we did before. But what about all the other nodes here? Are they also roots? Let's just quickly check. Well, for this one, 1, 2, 3. So nope, it does not have a height of 2. It has a height of 3. It cannot be the root. And just because of symmetry, the rest of these are also kind of ruled out. But intuitively, what we kind of learned is these outer layers are indicative of something. Perhaps instead of going from the middle and going out, we can go from the out and go in to the middle. This is the first solution I want to show you, and it is relatively simple to code up in my opinion, because what we do here is we notice just observationally what is different about these nodes and this node and even this node compared to these two nodes. Well, it's the number of edges. I mean, of course, this one has a ton of edges, but this one has 2 edges in 2 directions, but all the rest of these just have a single edge. Therefore, in terms of a tree, they can be considered leaves. This is where we start. We identify these outermost nodes, and we do so based on the number of edges the nodes have. These ones only have a single edge. Of course, every node in the graph is going to have at least 1 edge, because it is a connected graph, but not every node is going to have exactly 1 edge. We start with these nodes, and what we do is we rule them out. We know that the outermost nodes cannot be the root of the tree. Just like if you think about it in terms of like a straight line like this, of course, the endpoints cannot be the middle of the list. In a sense, we're looking for the middle of this graph. Now we've done that, and now we have 2 nodes remaining. Now we could do it again. We could rule out these 2 nodes, but then we'd be left with nothing. So what we say is, since we have these 2 remaining, this is our result. And just to kind of rewind a little bit, the reason we'd be able to identify these 2 middle nodes, what we would say is, as we went through every outer node, we're going to kind of chop off the edge. So for this node, we would get rid of this edge. So it originally had 2 edges connected to it. Now it's only going to have 1. This node had 1, 2, 3, 4, 5, 6, 7 edges connected to it, but we took out 1, 2, 3, 4, 5, and 6. Boom, 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 and boom, boom. So we took 6, and now there's only going to be one edge connected to this, and it would be the one right over here on the right. At this point, our graph is pretty symmetrical, and so we would return this as the result. This brings me to a important point, which is that even though they tell us to return a list of the roots that minimize the height of the trees, there's only going to be at most 2 roots that do that. There might only be 1 root, or there might be 2 roots. There's never going to be more than 2 roots. I won't go super in depth into why, but I think it's somewhat intuitive when you kind of draw it out and just think about the examples. Think about if we have just a single node remaining, of course, that's going to be the root that minimizes the tree. If we have 2 nodes remaining, well, both of them kind of minimize it. It's symmetrical, right? Now, if we have 3 nodes, this is the only way to draw it. I could technically draw it like this, but it's still a straight line, isn't it? So with 3 nodes, they can't all be the root of the tree. It's just not possible. So we'd have to remove these 2, and then we'd be left with 1. And the same thing when you have 4 nodes, whether it's like this or you draw them in a line, you're going to end up minimizing it to either 2 nodes remaining or 1 node remaining if you get rid of it like this. So I think this is a really key observation to make to be able to solve this problem efficiently, that there's only going to be at most 2 roots of the tree. There are many lines of logic that will help you arrive at this. So this is the solution I am going to code up. So if you want to see the code for this, you can skip to that. But I also wanted to quickly show you a slightly different way to solve the problem, at least conceptually. I won't explain the intuition of this approach too much, but I'll quickly walk through it and then explain why it works a little bit after that. So the idea is we pick any node. I won't pick the middle node just to kind of make it more interesting. I'll pick a random one over here. We pick any node, and what we say is we run a DFS or a BFS. We try to find the longest path starting from this node. It could go here or here, but interestingly enough, it's going to take us to this node over here. The distance of this path, if you just count the edges, is going to be 3. 1, 2, 3. Once we do that, the node that we arrive at is going to be a special node. And the reason for that is because we know with 100% certainty that this node is going to be included in the longest path in this graph globally. When we started here, we don't necessarily know that this node is going to be included in the longest path, but we know for sure that the node that we arrive at is going to be for sure, because we picked this one randomly. Remember, we just picked it arbitrarily. We just chose it. And a little bit of the intuition here. What if I added another node over here? Right now, this is obvious, right? This took us here, and it's kind of obvious that this is included in the longest path, which, by the way, is going to be any of the paths. It could be this is of length 3. It's also this. It's also this. But if I add a node here now, it's more interesting. If I start here, I can take this path. It's of length 3, and I can also take this path. It's of length 3. So which one do we pick? It doesn't matter, because both of these are the longest path starting from here. And so by saying that, we guarantee that both of these nodes would be included in the longest global path. So regardless of whether we arrive at this one or we pick this one, watch what happens. We're trying to find the longest path now starting from here. And it's going to be 1, 2, 3, 4. If we started from here, it'd be the same thing. 1, 2, 3, 4. And at this point, it would be similar to the solution I showed previously. So once we pick one of the nodes and we guarantee that this is included in the longest path, now we want to find the longest path, and it's going to be this of length 4, because remember, all the other paths are of length 3, so this one is special, it's of length 4. Now we basically start at the endpoints and then move towards the middle. So get rid of this, okay, now we go here and here, get rid of these, and now we are here. So along that path, it had 5 nodes in it, and we chose the middle one over here, and that is the root. That minimizes the height of the tree. It makes sense why you'd want to go in the middle, doesn't it? Because that's how we would minimize it. If we were not going in the middle, it'd be kind of a lopsided tree like these, for example, whereas this minimizes it. It keeps it even. And just to convince you even more that this approach works, let's see what would happen if we actually made a three-way tie. So we add another node over here. So now this could either go there, or it could go there, or it could go there. There's three choices. Well, it doesn't matter, because even though now there are multiple longest paths, this one of length 4, this one of length 4, and this one of length 4, notice how all of them converge at the middle. So this is the intuition of this approach. If you were to code it up, you'd basically run either DFS twice or BFS twice, and your goal would basically be to find one of these longest paths. So whether it's like this one, for example, you'd get this path, you'd have a starting point and an ending point, and then you'd basically get the middle, whether it's one node or it is two nodes in the middle. So if you got rid of this, it'd be these two nodes, then you'd return those nodes. But that's more complicated in my opinion to code up. So I'm going to stick with the first approach I showed you. The first thing, after all that complicated stuff, we're actually going to start with something easy. We're going to build a adjacency list for the input that we're given, because we're just given the pairs of edges. Like each edge is just connecting two nodes, but we want to be able to map a node to all of its neighbors, because that's going to be pretty important. So we're going to create a default dictionary of list, and we're going to go through every edge. So node 1, node 2 in the edges. So we're just unpacking the pair. We're going to say for neighbor, or for node 1, let's append its neighbor node 2, and do the same thing in the opposite direction. So node 2 has neighbor 1. Now is where we kind of count the edges for every single node. If you're familiar with topological sort, this is similar to that algorithm. At least this is one variation. We're going to count the number of edges. We're going to do that in a map. So we're going to say for every single node, we want to count its edges. How do we do that? It's actually pretty simple, because we created an adjacency list, which we're going to need later in the problem, but it's also going to be useful here. So for every node, let's say source neighbors in the adjacency list, and we can unpack the items like this. We're going to say that if the number of neighbors that this node has is equal to 1, then that means it's a leaf node. It's something special. And so we're actually going to declare a separate variable for that. We're not going to just make it a list. We're actually going to make it a queue. In Python, you can do that like this. This part won't be super complicated. You'll see why I did this when we continue the rest of the algorithm. But if you wanted to, you could leave it as a list for now. But I think it's pretty clear why we want to start with the leaf nodes, because we're going to go layer by layer into the middle of the graph/tree, just like this. If they have a single neighbor, then they must be leaves. So we'll say leaves.append the source. Regardless of whether it's a leaf or not, we do want to count the number of edges for every single node. So we'll say edge count for this is going to be length of its neighbors. Great. Now is where we basically go layer by layer. This is why we had a queue here, because while our queue is non-empty, we are going to go layer by layer. So we're going to go through an individual layer like this for I in range length of leaves. Just so you know, in Python, this is the equivalent of doing this, taking a snapshot of the number of leaves here and then doing this. So in most languages, this is not the case, but in Python, this is equivalent to what I had here. And the reason for that is because range is actually a function. It's only going to be called a single time. So whatever value we pass into it is what this is going to end up being, and then we'll enumerate that many times. The reason that's important is because inside of this loop, we are actually going to be modifying the leaves queue. We're going to be adding to it and removing from it. So we want to take a snapshot of the length before we execute this loop. So now we pick a node in the outermost layer and we pop it. We say leaves.pop left, and we get the node. And then we will go through the neighbors of that node. Why are we doing that? Because we want to update the edge count. Remember, we want to now identify the new nodes that are on the outermost layer. For us to do that, we say that, okay, if this outermost node, or this node, has been removed, then its neighbor must have lost an edge. So we can say this, edge count of the neighbor goes down by 1. And the very convenient thing is only the nodes that lost a neighbor have a chance of becoming leaves. So we don't have to brute force it. We don't have to go through every single node in edge count. All we have to do is say, if a node lost an edge right now, let's just check, is the edge count now equal to 1? If it is, then we know it has become a leaf. So what we would say is leaves.append right the neighbor. Maybe it's still greater than 1. That would be fine. We would just skip this part. This is kind of the core part of the algorithm. The only thing we're missing here is the terminating condition. When do we return? How do we return? How do we know we can stop? Well, we're probably never going to go until this is empty, because then we'd be left with an empty graph, right? One thing we want to do is keep track of how many nodes we have left, like how many nodes that we haven't visited in the adjacency list, that we haven't removed from a layer. So we're going to conveniently use the variable that they gave us. N is the number of nodes we started with. Every time we pop from the queue, let's just decrement n by 1. We know we can stop when we're out a layer. We're at a layer here, and n is less than or equal to 2. That means the total number of nodes is less than or equal to 2. The total number of nodes remaining, not the total number of nodes in leaves. That would be the outermost layer. It could be possible that the outermost layer has 1 or 2 nodes, but the total number of nodes is still greater than that. So we want n to be less than or equal to 2. If that's the case, what do? Well, we can return whatever the remaining nodes happen to be, and they are going to be in leaves. That's a queue though, so we can convert it to a list in Python just like this. And this is the entire code. So it's not, super crazy, nothing super complicated that we're doing here, just building an adjacency list, counting the in degree of every single node, the number of neighbors every single node has, and then running a relatively simple breadth first search. In my opinion, probably the hardest part of this is just knowing that there's going to be less than or equal to 2 nodes. There's going to be only 2 nodes that are the minimum height trees. Okay, a very, very sloppy mistake on my part. I apologize. So here we're checking if edge count is equal to 1. I don't know why I did that. I pretty much just forgot to put the neighbor here. We want the edge count of that neighbor and checking if it's equal to 1. So now let's run the code. And this is actually a good bug, and I'm kind of glad I did this live. So just to show you that it's not magic. So we actually missed an edge case. It's the last case here. That tells me maybe Leetcode actually missed it the first time that they created this problem and then only added it later. But can you recognize why we missed this? So if n is equal to 1 and we have no edges, which is going to be required if we have exactly 1 node, then we're going to have 0 edges. And we return an empty list, but the expected output is actually this. I think our solution actually never really returns, because this loop would not execute. This would then not execute either. And then of course leaves would be empty, so this would not execute either. So that's a problem, and that's only going to happen if we have 0 edges. And if we have 0 edges, then we must have 1 node. So the easiest way to check for this is just add an if statement. If n is equal to 1, then return an array with the value 0. Why do we return the value 0? Because remember that nodes are numbered from 0 to n minus 1. You also could just check if edges is empty like this, but they are actually equivalent, because we know we're always going to have exactly 1 more node than we have edges. So let's take this code and run it. Now you can see we pass, and it's a relatively efficient solution. If you're preparing for coding interviews, check out leetcode.io. Thanks for watching, and I'll see you soon.